All right, this is for my computer science final, and I'm going to be showing off my 6-bit stack calculator in Minecraft. Basics. Minecraft uses wires and inverters. With these, we can actually do just about anything. In the real world, this doesn't quite work this way because of how voltage works, but the ideas and concepts are still the same. So we have a wire here, right? And we have inverters here. So we toggle these off, the output turns on. We can use these to create an AND gate. So we need to turn this input on, this input on, and we get an on output. We also have an XOR gate. And there's many ways to do these, but this is just a simple one that I found. In this project, we're going to be representing bits, numbers with bits in binary. So let's go ahead and represent, this is going to be 8 plus 1 is 9, or let's go 11, which is actually going to be B in hexadecimal, which will come in handy later. This right here is a full adder. It takes in 2 bits and a carry bit, and it outputs the sum and the carry out. We'll go over this later when we get to that. We have basic memory. This is very similar, very close to how that other memory circuit works. Actually, it's the exact same if you just move some of the pieces. But yeah, one important thing is going to be encoders and decoders. We have to be able to take a value and encode it into bits. So we got 1, 2, 3, 4. So 3 right here is going to be encoded by 1, 1. Sorry, 0, 1, 1. And you can actually see we encode it there. It comes out, decode it to here. So we want to do this value. 1, 0, 0, 1. It's going to be decoded over here. So this is that circuit. Similarly, if we're going to be building a calculator, we need to have control over where information goes. So the red here is the bus. It's a system component that runs throughout the length of basically the entire computer, and it needs to be very specific in what values it accepts onto it and which values it doesn't. So right here, the bus is actually disabled. Let's say we want to have, let's say this is like a register or some user input, and we need to write it to the bus so that some other component can read it. We have to enable the output for this bus. And so if we have multiple of these and some logic determining which of these, we'll use a decoder actually to pick between, let's say we had 8 registers, we'll be picking between one of those, all 8 of those registers, we need to pick one of them to have the output read from. And so this is that system. This is how we build a mux. This is the basic component. Finally, this is our memory cell. We can write something to the memory cell. Let's go ahead and write this bit and write enable. Boom. So very simple, very obvious how this works. Well, the red sum maybe not, but black box, it makes sense. Write enable, value gets stored. Up here, the bus is represented by these bits here that run down, and we have our outputs on this side. So this right here is actually going to be like one register there and one register here. So between those lights or something like that. Actually, you can see up here where they're broken up. But this is multiple different registers, and they all have their own write enable bit line that we can enable. So let's say we want to write, let's write all zeros because they all have something on them. This will make it easy to see. Go ahead and write it to that one. You can follow that all the way down, so that's at the very end. It appears there's an issue with this one, although luckily we're not actually using this one. I'm pretty sure I fixed that, but you can see the idea. We wrote the bits to this farthest register. Just ignore that. All right, so here's the plan. We're going to have our stack. It's going to be 8 bytes. Not quite bytes. There's 6 bits each, but 8 different values stored in our registers. And we're going to have a program controller that decides which of these we're reading and writing from using a decoder and a write enable bit. The user is going to input values. They're going to get stored on the stack depending on where the program controller is pointing to, and those values are immediately going to be output onto the output bus and displayed. Later down the line, once we have values stacked up in here, the program controller is going to execute instructions. What that's going to look like is we're going to be loading some value into the R1. We're going to decrement the program controller. We're going to load some value into R2. They're going to execute via whichever instruction we're supposed to do and put it onto the output bus, which is going to get immediately stored back in where the value should be stored in the previous register. And then that's automatically going to be displayed. So that's the kind of basic logic for the system. And user input's going to be, we're going to have systems as well that work with the controller to decide whether we're using input or ALU to put onto the input bus. There's a whole bunch of little quirks and control circuits that we need to use. But this is the basic idea of how a stack calculator works. I think the best way to do this is give an example of a calculation going through and showing the parts and pieces. So let's start by writing a value. Let's pick, I don't know, let's pick 10. So this is going to be represented by hexadecimal A. No, let's not pick 10. Let's pick 6. Let's pick 7. We're going to write 7 to 0th. This is the 0th because this is counting from 0. But we can see we wrote it to there. Let's go through how that happened. When we click this button, we are temporarily enabling this line to be sent through, and data gets sent up. This is the input bus that goes to the read side of our data line, of our registers here. So you can actually see the 8 registers broken up by the yellow there. 1, 2, 3, 4, 5, 6, 7, 8. I don't know exactly which ones are which numbers, but they do work. So we got our data coming up and sent down there, and we need to pick which register we're going to save the data to. So in this case, we're picking the 0th one, and you can actually see this orange control circuit controls which register we're writing to at the time, which register is selected by the program counter. So right now we have the 0th one selected because all 3 of these bits are 0. The redstone's not on. We can see this represented down here on the green by all of these being on except for this one, which means that this is the 0th. This is the 0th register. So that comes up to here, and it allows the write enable bit, whenever the write enable bit's set, to write only to that register, and it allows the read bit for that register to be set, and set in this case is off because of how the system works. But yeah, so we can actually see that our value got sent in here. When we push the button, we can actually see the yellow. We push the right button right here. The yellow comes up, gets sent to here, goes into the circuitry. This is similar to the mux. It actually is a mux. It allows only this one because this is the only one that has its value off here. This is hard to see what's happening, but it does work, and we can actually, let's see it. So if we push the button here, right now we have our 0th register selected. If I push this button and we're quick, we actually can see the torch turn off. You see it right there. All the other torches didn't do that. It's just this one, or all the other torches here at least didn't do that. And so what that means is we just wrote the value. We overwrote it. It's the same thing though. So 7, you can actually see 1, 2, 4. That's 7 on this first register, which is output already here, and output down there onto the screen. So our first one has a 7 in it. Let's go ahead and add some value here. Let's make it a, I'm going to make it a smaller number so that we can subtract it from 7. So let's make it 2. When I push this button, we have a program counter down here in the blue, which is only 3 bits because there's only 8 registers. We have its own addition system. This is very hard to explain, but we have our registers coming up here, and you can actually see that now a different register is selected. So rather than being the first, the 0th one, it's the first one that we're writing to and reading from. Let's go ahead and write that value. Right now there's something else, some other junk in there, but we're going to write the value 2. So now we have data stored in our buses. How do we execute an instruction? To start with, we're going to read the value from the currently selected register down, and it's going to get stored into a temporary register. After that, we're going to decrement the counter via this mechanism, this monstrosity. And we're going to save the second value down here. So first we'd pull the 2 down, we'd decrement the program, and we'd store the 7 down here. Next what's going to happen, these get put over to here and get sent into our adders. So the way these work is you get every value goes to every other one, so this is the least significant bit of the top register, and this is the least significant bit of the bottom register down here. They get sent through and added. So we have our 2 inputs and a carry in, carry in, carry in, carry in, and we get our output on the bus right here, which gets sent back up to there. The way we do a subtract instruction, if you remember in binary, we can represent a negative number by flipping all the bits and adding 1. Same thing here. So right now the subtract instruction is currently set. What that looks like is doing this. So right now we're adding. Now this wire is the determines what mode we're in. So this is subtraction. What we do is we take the value, we invert it all. So if you notice, every other one of these is inverted from what it was back there. So this one's on, gets inverted, it's off here. This one's off, gets turned on here. So these are all, I guess these are all XOR gates. And as well as that, whenever we're in subtract, this is going to be off, turning this on, and we carry in the 1. We carry in a 1, which is identical to a subtract instruction. Data then will be pushed up onto the input bus here, sent down there, and stored. And if you remember, we already decremented the program counter, not the program counter, the program controller, and so we'll be storing it in the previous memory slot, which is what we want. So, from my point of view, this is what this is going to look like. Let's go ahead and set the subtract bit to on. So we are subtracting. We're going to be subtracting 2 from 7. Execute. There we go. I was concerned for a second. It takes some time to get through all the circuits, but it does work. So, after executing our first instruction, we have a 5. Let's go ahead and add 5 to that. Again, so increment to the next one. Go ahead, write it to there. Takes a second, there you go, and add. So we're going to pop it off, put it into there. And boom, 5 plus 5 in binary should be A, perfect. If we add 5 again, we're going to get 15. Let's add 6. So increment to the next register, add it. I might have been too fast, I might have messed it up, we'll see. So we got 6 in that, looks like it's good. And let's go ahead and add again. So this should roll over to 10 plus 6 is 16 hexadecimal. It's going to be represented by 1, 0. Perfect. So we got 16 stored. Let's go ahead and subtract 15 from this. So increment to the second one here, and we are going to store it to the register, put it in subtract mode, and boom, go. So 16 minus E should be 2. Yeah, no, that makes sense. And yeah, so this is my stack calculator in Minecraft.